Assalamu alaikum. My name is Mohammad Sajjad Hasan Towfiq. Today I will present my project, the Smart Energy Management System. This is an engineering solution designed to reduce electricity waste and improve energy efficiency in households using smart automation technology. The main purpose of this project is to reduce unnecessary electricity consumption in households. Our four key goals are: first, to lower the electricity bill; second, to reduce power consumption when devices are not needed; third, to promote smart uses of appliances; and fourth, to support sustainable energy use. In short, we want homes to be smarter about how they use energy. The core problem is this: in many homes, electrical devices like lights, fans, and air conditioners remain on even when nobody is in the room. This happens because people forget to turn them off, or there is simply no automatic system to do it. The effects of this problem are serious. It causes high electricity bills, wastes a large amount of energy, puts extra load on the power grid, and contributes to environmental pollution. This is a complex engineering problem because it involves multiple factors: human behavior, energy patterns, cost, and technology. And there is no single obvious solution. To solve this problem properly, we first gathered information from several sources. We studied appliances usage patterns, when and how devices are used in different rooms throughout the day. We also collected energy consumption data to understand where waste is highest. We analyzed user behavior when rooms are typically empty and studied existing smart home systems. Finally, we reviewed sensor technologies and estimated the cost and feasibility of different components. We considered three possible solutions to this problem. The first was a manual switching system, simply having users turn devices on and off themselves. This has low efficiency because it depends entirely on human memory and discipline. The second was a timer-based control system. Devices turn on and off at present times. This is better, but it cannot react to real conditions. If someone is home earlier or late, it fails. The third option was a sensor-based smart system, which automatically detects whether a person is present and controls device accordingly. This is the most efficient and practical solution. We selected the sensor-based smart energy management system for four main reasons. First, it is fully automatic. No human efforts is needed. Second, it is energy efficient. It reduces consumption by approximately 40%. Third, it is user-friendly. People don't need to do anything special. And fourth, it is cost-effective. Low operating cost and high long-term savings. This is why the sensor-based system is clearly the best engineering choice. Now let me explain the system design using this block diagram. On the left side, we have the input, two sensors. The motion sensor detects if a person is present in the room. The current sensor measures how much power the appliances are using. In the center is the controller, the microcontroller, which can be an Arduino or ESP32. It receives data from the sensors, runs the decision algorithm, and sends control signals. On the right side is the output, a smart relay switch that physically turns devices on or off. The appliances, lights, fans, and other devices are connected to the relay. The system also has a power supply and an optional mobile app for remote monitoring. And importantly, there is a continuous monitoring loop. The system never stops checking. Let me now describe each component in detail. The motion sensor, especially a PIR sensor, detects human presence in the room. It sends a signal to the controller when it detects movement. The current sensor measures the power draw of connected appliances. It helps track energy consumption in real time. The microcontroller, Arduino or ESP8266 or ESP32, is the brain of this system. It reads sensor data, runs the algorithm, and controls the relay. The smart relay switch acts like an automatic power switch. When the controller signals it, it either opens or closes the circuit to turn devices on or off. Power comes from the main electricity supply with an optional battery backup for uninterrupted operation. The system works in an continuous 6-step cycle. Step 1. Sensors detect whether a person is present and how much power is being used. Step 2. The microcontroller processes the sensor's data in real time. Step 3 is the key decision. If no motion is detected, the relay turns off the appliances. If motion is detected, the appliances continue working normally. Step 4. Energy usage is tracked and logged throughout. Step 5. Optionally, this data is sent to a mobile app so the user can monitor consumption remotely. Step 6. The system waits briefly and then repeats the entire process again continuously, 24 hours a day. This flowchart shows the decision logic of our algorithm visually. The system starts initialized and then reads sensor data. It then asks if motion is detected. If the answer is no, devices are turned off automatically. If the answer is yes, devices are allowed to continue operating. In both cases, energy usage is tracked. The system then checks whether to send data to the mobile app, then waits for the next cycle. Finally, it checks if the system is still on. If yes, it loops back and repeats. If no, it stops cleanly. This loop continues as long as the system is powered, making it truly automatic and continuous solution. The system is implemented in 6 phases over 10 days total. Phase 1 takes 2 days to identify all targets room and list the appliances to control. Phase 2 takes 2 days to physically install the sensors and relay switches in each room. Phase 3 takes 1 day to connect all components to the microcontroller. Phase 4 takes 2 days to program and upload the automation logic. Phase 5 is 2 days of testing. We verify detection accuracy, switching reliability, and energy logging. Finally, phase 6 is 1 day for the final deployment in the real environment. To evaluate the system, we compare energy consumption before and after installation. Looking at this chart, we can see significant reduction in all rooms. For example, the living room dropped from 120 kilowatt hour to 72 kilowatt hour, nearly a 40% reduction. Similar savings were seen in the bedroom, kitchen, and office. Our key metrics are approximately 40% energy reduction, less than 1 second system response time, 24/7 continuous monitoring, and 100% automatic control with no human intervention needed. These results confirm that the system achieves its goal. The system has 4 main advantages. It reduces electricity bills, it saves energy without any user efforts, it is environmental friendly by reducing carbon emissions, and it improves overall efficiency. In terms of risk factors, we must acknowledge that sensors can malfunction. There is an initial installation cost, and the system requires periodic maintenance. However, these are manageable challenges that do not outweigh the long-term benefits. For future upgrades, we plan to add a mobile app for remote control, AI-based prediction to learn user patterns, voice assistant integration with Alexa or Google Home, and eventually solar energy integration for a fully sustainable system. In conclusion, the smart energy management system is an effective and practical engineering solution to reduce energy waste in household. By combining motion sensors, current sensors, and a microcontroller, the system automatically manages appliances, saving energy, lowering electricity bill, and contributing to a sustainable future. This project addresses a real problem using real engineering, sensors, controllers, algorithm, and testing. Thank you very much for your attention.